Recording in progress.
All right, folks, welcome back to our conversations in Chem 220. This one is a new topic for us, which is not the why, the how of chemical reactions happen. So if thermodynamics is the why, like why does anything happen at all? And we know now it's because of its free energy to change. Then the kinetics is the how, meaning how does a chemical reaction proceed across time? And if we're talking about changes over time, then we're fundamentally talking about a rate. So our next topic in Chem 220 is this notion of kinetics and how we model the rate of reaction or how the reaction proceeds across time. Before we can even talk about like a rate or models, this is going to get really mathematical and graphical. Let's begin with something that is kind of like our best theory or understanding of how chemical reactions occur like in the first place. So there's like the thermodynamics of why they occur in the first place. And now we're talking about like, well, what is it that is happening when a chemical reaction happens? Like what are we looking at here? So when we have that conversation of what is going on in a chemical reaction, we are looking at the collision model. So let's define the collision model of chemical reactions. You will find that the collision model of reactions is actually very similar to our kinetic molecular theory of gases, right? It's an understanding that when we think about molecules, those molecules are in a constant state of motion unless they're bound up in some kind of like ionic solid, right? So the collision model says that a chemical reaction occurs if and only if, so IFF, if and only if, certain conditions are met. So the first is that our reactant molecules, and you know what, let's just call them molecules. Or if we're looking at like a monoatomic gas, they must first collide. So they've got to smack into one another. So there has to be like a physical encounter. And they don't just collide and then react. They have to like have, like I said, a certain set of conditions. So molecules must collide. They have to encounter one another physically in space. And they have to collide in the correct orientation, meaning like their position, shape, and direction of impact matters. And lastly, they also must collide with a sufficient amount of energy to prompt the breaking of bonds. So it's kind of like, I don't know, imagine that you are walking on the street and like you very gently just kind of like bump into someone, right? That is not enough energy that you were carrying to like break that person off the sidewalk, right? However, if you are out on a jog and you run into someone with like all of that kinetic energy gets transferred to that person, and that person is broken away from the sidewalk. So their bonds have been broken. That would be considered like a sufficient amount of energy in the collision between you and that person. So sufficient amount of energy. And again, this is related to the idea of breaking the original chemical bonds. So in this example here, we are looking at a model of the reaction between carbon monoxide and oxygen. So this is our gas phase reaction. You can see we have a bunch of oxygen molecules modeled here as these red molecules. We've got larger molecules in front to indicate that they're closer, smaller molecules in the back to indicate that they're farther away. So this is trying to show some kind of like three-dimensionality to how these molecules are moving through space. And then we have carbon monoxide with the black and red. So let's look at two possible scenarios. So we are going to assume that 1 and 3 both happen, meaning we are going to assume that our molecules are going to find one another in 3D space and run into one another. And then we are also going to assume that once they run into one another, the amount of energy that's transferred from one molecule to the other is enough to break the bonds that were initially present. So here we are looking at condition 2, meaning why does orientation matter? So let's think about what products could be formed. So this reaction, we know, is modeled to form CO2 and O. So if we're going to form CO2, what we need to do is we need to be oriented in a way that when we collide with enough energy to sever the bond between our oxygen atoms, that we result in an actual three-dimensional shaping that creates CO2, where CO2 is a carbon flanked on either side by oxygen atoms. So we can look at scenario A, where we have this kind of like oxygen to oxygen collision. In this scenario, we've got enough energy to break the bond, right? We are encountering one another in 3D space. However, the alignment of atoms here does not form CO2. So this collision does not result in a reaction. So we cannot make CO2 by doing carbon, then oxygen, then oxygen. It's not how that works. That's carbon, oxygen, and oxygen. However, if we do have our molecules that collide in 3D space where we have the orientation that allows an oxygen to be given to carbon by severing its bond with O2, then that is going to result in a reaction, right? We do have the correct product here. So we are indeed able to form products, right? The reaction happens. So anytime we are talking about a rate of reaction, keep this model in the back of your head. We have to ask ourselves what things are going to be affecting these collisions, what things can be formed as a result of these collisions. And here we're saying, like, what are the assumptions that we're going to be making about these collisions? So we're assuming that in order for a reaction to happen, we have to have molecules that smack into one another in the exact right orientation and with the exact right amount of energy to allow those bonds to break and for new bonds to form. So that's the collision model. In our last point, point 3, what is that energy that's needed to break our chemical bonds and begin to form products? Well, we have a name for this. This is called the activation energy. So the activation energy is the minimum amount of energy needed for the reactant molecules to collide and sever bonds to form what we call an activated complex or an intermediate complex, or like a transition state complex, anything that implies like this is something that's happening when the reaction is not yet complete. And the thing about activation energy is whether the reaction is endergonic or exergonic, all reactions require this amount of energy. We can't just have chemical bonds that break or sever without any kind of energetic input, right? Then things wouldn't exist as molecules. Substances would not stay together. So when we talk about ender versus exergonic, we're talking about the net difference between our reactant and our product energy state. That's what makes us a state function. So when we were talking delta G, here it looks like we had some G reactants, and down here, G products. And the change in that is a downward change, right? We started off with a high amount of free energy, wound up with a lower amount of free energy. So the system itself, the reactant molecules, had to emit free energy to do work elsewhere in the surroundings. So we would say that delta G is negative. So this is exergonic. And this depends only on initial and final states, meaning reactant and product states. And the reason why we have that delta is exactly that, for that reason, right? If we're just looking at the change from going from reactant to product or start to final, we just want to compare those two states. That's what makes a state function and allows us to do something like calculating difference. So we don't care about how we got there. That's the thermodynamics, is just where do we start and where do we wind up. Now, when talking about chemical kinetics, we are very concerned with how did we get to where we are? So not just like energetic wise, but also like structurally, three-dimensionally, what is happening in our reaction? So here we are looking at a different reaction. We are looking at a reaction of carbon monoxide gas with NO2. These react to form CO2 and NO. The activation energy is the amount of energy that is needed, like this little amount of energy here, this slope. Shouldn't say slope, this like increase, this rise. Meaning the difference between our reactant energy state and like the most unstable state of the reaction, that's the activation energy. How is it that we can go from having carbon monoxide separate from NO2 to now having this like real close association just before the bonds are broken, reformed, etc.? And that point in the reaction at which we have formed this activated complex, this is the highest energy point in the reaction because this is unstable. And we would hope it's unstable because we would want to have the transfer of oxygen actually happen so that we wind up with the products. So if we were looking at thermodynamics, we're looking here, but this little hump here, this little hill, this little barrier is the activation energy. So this is the energy needed to achieve this like unstable just before bonds are severed. So it's here. I should probably change this. The minimum amount of energy needed for reactant molecules to collide and begin severing and reforming bonds that form our activated complex. So that's what activation energy is. Minimum amount of energy needed to make the most unstable intermediary thing in our reaction. So in these examples here, this would be the point at which we actually do have like carbon touching an oxygen atom here. This would be the transition state complex, the intermediary complex, the activated complex. That would be the most unstable thing. All right. Let's talk now about the rate of chemical reactions. Now that we understand that reactions happen because of collisions between molecules, and that collisions between molecules must occur with a specific orientation, as well as a certain amount of energy needed to meet that transition state complex. So let's define the rate of a chemical reaction, capital R. This is how fast a reaction proceeds or happens. So we are now thinking about time as a component here. And you can think about a rate of reaction in a couple of different ways. It is the rate of consumption of reactant or formation of product over some time t during the reaction. So let's look at an example here. Let's say that I've got A that is reacting to form B. We know from our study of equilibrium, the point at which the rates are equal is when we're at equilibrium. This is not the right graph for that, but let's make a note here. When the rate of the forward is equal to the rate of the reverse, and we are at equilibrium. And if I wanted to track how much A was changing over time, I could do that a couple of ways. I could do something like look at its initial concentration at time equals 0, so just before the reaction happens. and compare that to the amount of reactant at time equals, I don't know, T. And by looking at the difference between these two, or the slope that connects these two, which would be delta concentration A over change in time, I would be able to get the average rate over time interval from 0 to T seconds. We could do the same thing with our products. Like I could look, I don't know, at any point in time. Let's call it T1. Look at the concentration of reactant B. And then compare that to some time T2, where I have some concentration of reactant that is now higher. If I were to connect these 2 points, I would be looking at a change in the concentration of B over some time interval delta T, which would be the average rate over time T1 to T2. However, as those of us who have taken calculus might notice, especially here in this example, the average rate is not always what we look for, right? Like we often want to know the rate of reaction at an exact point of time. So we use deltas to express changes over long time periods. These give us our average rates. However, if we want to know an instantaneous rate, meaning the rate at some exact time t. So for example, like what if I wanted to know the rate exactly at this point? Then I would need to use a derivative, meaning I would need to find at this point exactly what the slope of my line tangent to the curve is, because that will tell me the rate of change at that exact point. So this is what we call the instantaneous rate. It's the slope of the line tangent to our decay curve. And we express that using, from calculus, D. So I now have 2 different ways, well, 4, but I'm going to be thinking about instantaneous rates from this point forward. And we have now 2 different ways of expressing the instantaneous rate of reaction, either by looking at how A is going to be consumed or how B is going to be created. So if it helps you to view it this way, I'll choose green, hopefully it's not awful. You can see that the slope is very sharp for A when it begins to decrease. And then over time, that tangent line slope gets shallower and shallower, meaning that like the rate of change, the literal slope, rise over run, is getting smaller and smaller and smaller. So our rate is slowing down. Whereas we've got initial really fast rates here for the production of product, and similar things happens, right? Once we achieve then our point where our rates of forward and reverse are equal, then we're at equilibrium. So I'm going to write an expression for the rate for this reaction of A goes to B. I could say this is equal to the negative of the change in A at some instant, so dA, at some exact little infinite like point exactly in time, dt. And this is also equal to the instantaneous rate of change of B at that exact point. And we do include the negative sign for A because A is consumed. And we always express rates in terms of positive, right? So we always say like there is this amount of change in concentration per time. We don't say there's like a negative change, even though if you were to look at final minus initial, you would see that this would be final minus initial, smaller minus bigger. So that would be negative. But this is the idea here that we can look at the infinitesimally small change in A, or we could look at the rate expressed in terms of how quickly B is made. So this is the reaction rate. And again, this is an expression of how fast, thinking like how much has our concentration changed? How much of our reactant has been consumed over some time period or at some exact period of time, or how much product has been made over some time period or at some exact period in time. So this is an expression of the rate. Now that we've talked about what a rate of reaction is, and we understand that we're thinking about reaction as being collisions, let's talk about things that will affect or alter or augment the rate of reaction. So we are going to ask ourselves, what factors, what conditions, what can affect the ability of molecules to collide, meeting conditions 1 through 3, such that the rate of their collision is faster. So the first thing is we can do something like affect the temperature of our reaction. As we increase the T, there's more kinetic energy available for our molecules to use to move around with. So we have more collisions. Similar thing goes for pressure. If we're gaseous, we are assuming that liquids are not going to be affected, solids are not going to be affected. So as we increase the pressure, we're just increasing the statistical likelihood that we will have that perfect collision happen. And so it happens faster. We could also have something like concentration. More molecules means more collisions. And then we can also have something called a catalyst. So what catalysts do is very interesting. These are substances that are used but not consumed, meaning like the material that makes up those catalysts are not being used to make the products, right? Like they're not being disassembled and their atoms used as Legos to form products. They're like there as a mediator and then they go about their business. So catalysts, these are substances that are used but not consumed during a reaction. And what catalysts do is that they lower the activation energy barrier, meaning that it is now possible for more molecules to have that minimum amount of energy required, condition 3, to make that transition state. And how they do that is actually rather interesting. So let's just kind of put some end caps on this. So we've got temperature, we've got pressure, we've got concentration, and now we have catalysts. All right, so again, catalysts are very interesting substances. They are basically why it is any biological thing can happen in a timely manner. So these are substances that are used but not consumed during reaction. They lower the activation energy of the reaction, and they're able to do this because they change the actual mechanism of reaction, or like the pathway. So for simple molecules like carbon monoxide and oxygen gas, the pathway of those molecules finding one another is pretty straightforward, right? They're tiny little molecules, they smack around in the gaseous phase against the container that they're in, smack around, find one another, right? They're moving in these like little straight lines. That's our kinetic molecular theory of gases. So like that reaction pathway is just like you find one another and head-on collision. But if we think about something much more complex, like for example here, the splitting of peroxides in biochemical systems, because peroxides are really strong oxidizing agents and we don't want those around all of our things that are highly susceptible to electron transfer in our bodies. What these things can do, these catalysts can do, is they can actually facilitate the movement of particles, the movement of reagent through space such that they encounter one another faster. So in doing so, the activation energy is lowered. The molecule itself, the reactant molecule, has to carry like less energy because the catalyst is doing the legwork of ensuring that our reactant molecules can find one another in the first place. So for example here, looking at this reaction on the left of, where do I want to write this? X plus Y yields Z. Again, we can look at the difference in free energy between reactants and products. So this is exergonic. And if we were to look at the activation energy, or the difference between our reactant state and the transition complex, we see that in this particular general example, uncatalyzed, that amount of activation energy is quite large, right? That is a huge energy barrier in order for this reaction to happen, to occur. However, if you, being a reactant molecule or a biochemical system, bring in an enzyme, a catalyst, that will help maneuver your molecules through different pathways, then the highest energy pathway of that like new mechanism is going to be one that's a little bit lower than that in the original reaction. So here, this is now the activation energy with the catalyst. So it is less than, this would be our new reaction complex. which would include the catalyst. So for example, anything that's got like an H2O2, now it's not just H2O2, but it could be, that molecule is going to be bound up with peroxidase, and peroxidase is going to facilitate that molecule's oxidation and also like movement through your biological system, so that this reaction of like splitting apart peroxides is facilitated. It happens faster. That's what I mean when I say it's facilitated. And it was able to do that, happen faster, because at some point in this peroxidase's like mechanism of action, it created some transition complex state that was lower in activation energy or lower in energy difference required from the reactants than if the reaction were to proceed without it. So catalysts are very important. You will see catalysts that are non-biological, meaning like non-enzymes, a lot in OChem. So like we can use things like stick metals like platinum in our reactions that will then affect how molecules navigate around one another and thus affect the mechanism and happen a little bit faster, right? So yeah, these are the things that affect reaction rates. So this is kind of in like our comprehensive overview of like, what is a chemical reaction? How do we talk about how fast a reaction occurs? What things can affect how fast a reaction occurs? And specifically also like, what is going on in the middle of this like energetic initial and final state? That's what we care about as kineticists, right? So in our next video, we're going to talk about the Arrhenius equation, which directly correlates things like temperature and activation energy to the frequency of collisions, meaning like the rate of reaction. And then from there, we will go into what you and I as like experimental chemists care about, which is how do we model the rate of change of something over time? So how can I get a good idea of how the change in reactant concentration or how the change of product concentration is occurring when a reaction happens at a particular set of conditions? So that's coming up in our next few videos. Thanks.